Jay with another statics video, looking to save you guys some time and also shed some light on a little bit of an overwhelming problem this week, especially with spring break coming up. Anyway, so the first thing we want to do is look at the diagram and draw out some of the forces that are acting on our system. Don't forget, these are static questions. That means the equilibrium comes to zero. There's nothing going on, there's nothing moving, so we know everything is equal and opposite, which is great. Once we look through the problem description, we find some of the givens, except for one, which happens to be an Easter egg. That's cool. So you have to go through the emails that are in your history and find that the weight on this crane comes out to 3,200 pounds. So I thought that was cool that they hit that. Anyway, so our counterweight on this crane is 8,500. The weight of the cab, which is up here, plus the motor, is 2,400. The structure itself, which I'll touch on a little bit later, comes out to 5,500. It's not as straightforward as you think. And then we have this G-eval value, which is 32, blah, 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 blah. That comes in use in parts B and C, but right now, given that it's like 3 in the morning, I'm just gonna run through part A, and I'm gonna leave the calculations for B and C up here. If you wanna pause the video and take a look at them, I hope that they make sense. You can DM me and I can try to clarify that, but I really want some sleep. Anyway, moving on. So once we have this diagram up, and I'm going to touch a little bit more on this before I move on to the equation, what you're going to want to do is set it to equilibrium and solve through your distances to get to your answer. Now I'm going to walk through that process here real quick. Back to the diagram. Once we have our distances and our weights all labeled, what I've done here is actually drawn green arrows giving you a little bit of a visual where these forces are acting. Now you can see, obviously, most of the weights are acting down. Actually, all of them are acting down, I should say. The only forces that are acting up are these reacting forces. Just like the last video we were looking at, these reacting forces are what creates the equilibrium. We have this crane structure that's being pulled down by gravity. Now, that equilibrium comes from these solid structures pushing equally up. So when we have things like this counterweight, the cab, the structure's weight, the weight itself, everything that's pushing down, we have that equal force pushing up. Excuse me, and that's, you can see that in our equation here. So we have our givens, we have our diagram, we kind of have an idea of where the forces are acting. Now we need to move to our equation. The way you set up these equations is after you know where all the forces are coming from and where they're going and what they're being countered by, you can set up the positive values. You can create a point of reference if you want. I usually like my forces up as positive and down as negative. So in my equation, that's reflected. The y component and the y component of D, I should say the y component of C and D, are my positive values. And now the negative values are all these weights. The reason it's a y component is because y is up and down. The only forces we have to worry about, again, just like last statics problem, is the forces up and down. You don't have to worry about any side to side in this question. So now we have these positive upward forces. They're being countered by these 4 different weights. The weight attached to the crane, the structure, the counterweight, and the cab itself. Now the first thing we want to do after we get this equation is simplify it. Once we get all these weights combined, we get a 19,600, and then we have this minus the y component of C. Now we got that from subtracting it on this side and solving for dy, because that is our point of interest. We are looking to solve for the maximum force on dy. Now I'll touch on how we get that max part in just a second. I want to make sure that we're all here. Once we are all here, and if that makes sense, we want to start plugging in our distances. Remember last time when we had that distance point from our interest, we multiplied that by a weight? We're doing the exact same thing here. We're solving for D, but we're looking at C from this time, because we want to solve for C we want to get this value to solve for dy. And so we're looking here, and we have our first weight, which is that 3,200 pound weight, that literal weight on the crane. We know that this distance can fluctuate, but the cool thing about this first part is we're looking for maximum force. The reason this is important is because maximum force, and I'll kind of give you a little practical example. The reason we're looking for maximum force, or the way we should solve it, I should say, is we're going to plug in our maximum x distance. So think of it this way. You're in the crane yourself, and you have this heavy weight Just try to like practically imagine what it feels like when you move that weight out on your boom. It's gonna start pulling your crane down, and that's what we're doing here. The farther this weight's out, the more force you're gonna feel on this front pin, which is what we want. So we're gonna put this all the way out at x equals 86 feet, and we're gonna take our static equilibrium there. So that's what we're gonna plug into 3200. Then this 5500, which is the weight of the structure. Another point I want to give on this is that the weight of the structure is not in the center beam, it's actually at point G. Now it's given in the description of the problem. You want to make sure not to make that mistake. So when we get 55, we get this distance of 14, and you're like, oh, I don't see any 14 on the diagram. Well, that's because we're looking from point C, and you notice that the distance from C to the center boom here is 6 feet. And from the center boom to point G, which is that structure weight, is 8. That's where you get the 14 from. Now you're adding that 2400 times 5. Again, you're just looking at the cab, the distance from C. You have this 11 feet. And excuse my visual skewness here, I didn't really plan that drawing out. And that's where you get your 5. You just have the 6 feet and this 11 feet, and that's where your difference of 5 comes from. And again, you do that for the counterweight, and then you know that the y component of your point D creates that equilibrium when you add it. Now once you solve that last equation, you should get something around 21,500. And again, that's at that maximum distance of 86 feet. That's how you solve for D max. Now I'm not going to be able to go over parts B and C, but I'm going to move out of the way here, and you can pause the video and look through the calculations. Again, if there's any confusion, feel free to reach out to me or any members of the team, and we'll happily try to explain what we can in the time we have remaining. Good luck, and I hope this helped.